Right, okay, in this video we're going to look at Ohm's Law, and we're going to look at see if we can apply Ohm's Law to some circuit problems, and that'll probably be the next video. And in this video we're going to focus on is just the relationships that we can observe both physically and experimentally with Ohm's Law. So what is Ohm's Law? Ohm's Law is this equation here, V is equal to I times R. That's how it's written in your equation sheet. Hopefully you know that V is voltage, current, I, resistance. This idea of resistance you should have come across at GCSE because it's measured in ohms. You should hopefully know the unit of the resistance is ohms. We're going to talk a little bit more about what resistance is very shortly. Obviously current is in amps and voltage is in volts. So all of those things have their own units, and you need to make sure that those units are adhered to. Watch out for prefixes because they like to put prefixes, especially in current and especially in resistance. Resistances are generally large. We don't have small resistance, so you could have kilo ohms or something is a very common one. Also milliamps is a very common prefix for amps, and you need to watch out for that, of course. So milli times 10 to the minus 3, kilo times 10 to the 3 are common prefixes that come together there. So what is resistance then? Well, resistance is the idea about defining, well, essentially allows you to define how fast a current is going to move through something. If you imagine, and we'll do this demonstration in class, if you imagine a person trying to move through a crowd of people, then what happens is that person has to push through all of those people and so we pretend that this person is the electron and these guys are the ions. So there's a crowd of people and he's got to make his way through all those ions within a wire. And obviously it's kind of challenging because he's got to get around them, he's got to avoid them, and he's got to get through. So it takes him a little while to get from A to B. But what happens if we give him more energy? What happens if we give him more voltage? If the current stays the same, if the resistance stays the same, so i.e. the number of people or ions I have stays the same, then we would be expecting the current to increase as well if the resistance stays the same. So we would observe that. So if I give him more energy, he plows through there. Retrospectively, as you would expect, if as one person charges into another people, these people are very hot and bothered and upset about that. I don't know if you had anyone charge into you recently, but it doesn't make you very happy when someone does it. And so what happens is that we suggest that that's what the heat is caused from. So the heat, the more energy you put into these electrons to get them through those ions, the greater the current is going to be, and as a result you're going to get lots of collisions with these ions and you're going to generate heat as a result of that interaction. So retrospectively we could change this slightly and we could look at how resistance affects current by changing up this equation slightly. So if we say the current is equal to V over R, because that's how the equation works. So say what happens if we increase the resistance, so say we add more ions or people in this example, then what you have is a situation where this electron is going to have a hard time getting through all those people. We've upped the resistance. Where the voltage stays the same, what is this going to cause the current to do? Well, he's going to drop. Remember, current is the rate of flow of charge around a circuit. So in this case, he's not going to move through these people quick, he's going to move through them fairly slow. So as a result, the rate of flow of charge is going to drop. And that's a nice example of how resistance works. We can look graphically at this relationship, which is very important. Now, what you might not normally think to do is you've got a voltage against current for any kind of fixed resistor, and we are going to be looking at fixed resistors very shortly. and that is we use a straight line to represent what happens with a fixed resistor. Now, a fixed resistor is called a fixed resistor because it has a fixed resistance. How can we tell from this graph, V against I, that it's got a fixed resistance? Well, because the gradient is constant. Think about the calculation I'm doing here. If V is equal to I times R, that means that R is equal to V divided by I. What calculation would you be doing if you did the gradient of this graph? Well, you'd be doing the change in V over the change in I. And that is essentially resistance. So the gradient of this graph is the resistance, and where the gradient is a straight line, that means, the graph is a straight line, that means the gradient is constant, that means the resistance is constant, and that's a nice way of allowing you to work out the resistance. Somewhat problematically, however, experimentally when we do this, what we will see is that when you generally, in an experiment, you put what you're changing down here, which would be the voltage in this experiment, and the current is a byproduct of that. As we suggested in the first instance with the equation, when I said that when you up the voltage and you keep the resistance the same, that means the current would have to go up as well. So that's current is as a result of increased voltage. So that's why it's normally drawn that way around. Now the problem is that the gradient of this graph is not R. That's wrong. What is it actually? Well, it's a reciprocal. It's 1 over R. So when you work out this gradient, which is change in I over change in V, so I over V, that equals 1 over R. So in order to find out R, you just do 1 over the gradient. It'll give you the resistance of that fixed resistor. Okay, so that's the end of that video. Next video we'll look at how this is used in circuits and do some examples of that, and you'll get a chance to draw these graphs in lesson as well.